Hi, I'm Aaron Sampson, and in this course, I'll cover cloud services, delivery methods, security considerations, and networking services. I'll also cover cabling types, connectors, and Ethernet cable standards. Now, if you are using cloud services, this introduces the question of how you will connect from within your own on-premises organization to the cloud provider. So in this presentation, we'll take a look at a couple of options for doing so. But before getting to that, I would just like to address the term connectivity and what it means in this context. So let's imagine that you create your cloud subscription and you decide that you need to host a website or a web-based application. Of course, you can do so. So you might create a virtual machine to host the site or the application. And in terms of your customers, your business partners, and even your own users accessing the site or the application, they will just use a browser, standard internet connectivity. So that's all well and good, but that's not really what connectivity refers to in this context. If you are the administrator and or the developer of that site or application, then you need connectivity to the server. And let's scale this up. Imagine you have possibly dozens upon dozens of servers. Then you need those servers available to you, and you need them to behave more or less as if they were in your network. So to accomplish that kind of configuration, a VPN is certainly a viable option and perhaps one of the simpler options for connecting to the cloud provider. Typically, the cloud services offer VPN appliances or native software VPNs that you can use to ensure that all of those servers in the cloud are available to you on your network so that you can manage their resources, perform maintenance and updates and security patches, things along those lines. Now, of course, there are costs associated with this, but like all things cloud related, you only pay for what you use, but the cloud provider may charge for the total bandwidth transferred over that VPN. Now, another option is direct connection, and this can be implemented in a few different flavors, if you will, but this offers a more predictable connection. Typically, you'll see cloud providers using co-location facilities to offer direct private connections, and often those co-location facilities are telecom providers, people who already have communications infrastructure in place. So customers will then in turn rent these facilities from the data centers, and they will in turn offer a cross-connect back to the public cloud. So what you'll often find is that any given cloud service provider will offer this using this telecom provider or that one or this one or that one, and you can kind of browse through and find one that is appropriate for your area. But a lot of those telecom providers have these dedicated connections back to the public cloud providers. So in essence, they are reselling that service. Now, in this kind of configuration, of course, there are costs. The data center will charge for the cross-connect itself, and the cloud provider may still charge for the port. But once you have this, most providers will allow unlimited transfers over the direct connect. So this lowers the per gigabyte transfer cost. Now, there may be commitments involved as well, but the terms can be as short as 1 month. So generally, you don't have to lock into a multi-year contract or anything along those lines. So the immediate upfront cost might be higher, but given the fact that they generally offer unlimited transfers, this is where you start to see the savings, because if you're paying a per gigabyte fee, per month, then sooner or later that will probably cost more than this type of configuration. But of course, it always depends on the scale, how much data is going to actually cross that connection. And I should also mention, if it is a fairly small scale implementation, you may not need either of these. If, for example, you only have a few servers in the cloud hosting a few applications or services and you need to connect to them, you certainly can using something like remote desktop. You can simply connect to any given server and remotely administer it like any other one. It just might not give you very good access to the resources on that server, but it is generally fine for just administrative tasks. If you just need to, change some configuration options or implement an update or a patch or things along those lines, then that is still just regular internet connectivity. So like anything, as mentioned, it depends on the scale, but those are some of the methods available when you do need that more reliable connectivity to your cloud-based resources. Now, while cloud services can provide a number of benefits, it's not the kind of thing where you typically see organizations saying, all right, great, let's just immediately move everything to the cloud. It's usually a slow process, and there has to be a lot of investigation. Perhaps proof of concept has to be demonstrated, things along those lines. So in other words, before you do make a move to the cloud, you need to understand what's involved. And in most cases, that is knowing the risks. So in this presentation, we'll take a look at several of the risk factors at various levels and for various types of cloud implementations, beginning with IaaS, or Infrastructure as a Service. With this, you might have issues with legal transborder requirements. When you create any kind of cloud subscription, you really do not know where the data center is, or perhaps more specifically, where your data resides. And most of the larger providers tend to implement replication schemes to protect your data so that it is actually in multiple data centers, but that might actually involve that data crossing a border of some degree. So that is something you need to be aware of, and whether or not that is acceptable by your organization and or perhaps data privacy laws. Failure, of course, is always an issue. How isolated are you when it comes to any given failure? Because it is a multi-tenant environment. If this fails for that tenant, will it affect me? So you need to know what kind of isolation is in place. Backup and security measures, you certainly need to know what is being implemented there. Do they have intrusion detection systems and intrusion prevention systems? What are their disaster recovery procedures and or policies for making backups? And I'm not trying to suggest at all that these things aren't in place. In fact, for most of the large-scale providers, they are very much so in place. It's just a matter of knowing what they are. Same thing with the physical security. What kind of physical security do they offer at their data centers, and how do they handle data disposal? So again, these are all just things to consider. It's not that they aren't there. It's just that you need to know what they are and how these risks are mitigated. So then at the PaaS level, or Platform as a Service, there can be issues with application mapping. Theft and disclosure might occur. There can be SOA-related vulnerabilities. That's service-oriented architecture. You don't really know how the service is structured at the provider end, if you will. So there can be vulnerabilities there that you don't know about. Application disposal, what happens to the original? So as your versions increase and you move from ultimately testing to production, what happens to the original files and or any backups that were made? And then at the software as a service level, there can be questions about data ownership. Again, the data is not physically under your control. It resides who knows where. So there could be issues with ownership. And again, disposal becomes an issue. You need to ensure in many cases that it is properly disposed and that no one else can get a hold of your data. Software systems development lifecycle, what happens with respect, again, through the whole versioning history of applications. Identity and access management always has to be considered. Who looks after that kind of user management, for example? Broad exposure, there can be issues when it comes to any given application and or the data and or the users with respect to who is able to see what. There can be browser vulnerabilities because in most cases you are using a browser to access the application. And ultimately, you need to understand what kind of exit strategy can exist if and or when you are going to discontinue the service. Then with respect to the different types of clouds, when dealing with a public cloud, there can be issues with data pooling. The infrastructure is shared by multiple tenants, and tenants have no relations to other tenants or to any other enterprise. So there's no common concerns for the security of the data itself. In other words, my concerns aren't your concerns, and they aren't anyone else's concerns. So I am only concerned with my own interests. You are only concerned with your own interests, but those may not be compatible concerns. So how does the provider handle, in essence, trying to make everyone happy? Collateral damage and attack on one tenant could impact the other tenants. Again, if a portion of a service goes down, how isolated are you from that failure? So that whole idea, again, that any kind of attack can propagate. And if it's a private cloud, there can be issues with application compatibility. Older applications may not work with newer technologies, such as customized software. There certainly is a significant investment. It requires a certain skill set. Training, recruitment, and maintenance of the infrastructure is always necessary. So that is certainly a major consideration. Now, at least with a private cloud, things are more under your own control. But there are still these considerations. And then with the hybrid cloud, there can be issues, of course, with mixing two or more cloud types. This requires strict identity control and strong credential management, and still has risks such as unavailability of an application or data, loss, theft, disclosure. Anything along those lines can still happen within a hybrid cloud configuration. And finally, the community cloud. This involves sharing the cloud, so entities may have different security measures or requirements, even when belonging to the same enterprise. So a faulty procedure or service level agreement can render entities at risk. And there are, again, possible impacts in the areas of data loss, theft, or disclosure. So ultimately, there are always concerns. And I do want to stress the major cloud providers will make heavy investments into mitigating these risks as much as possible. In essence, they depend on that ability. So it's not a matter of them effectively saying, well, here is our service and here is how we can protect your interests. So it's just a matter of knowing what those concerns are and how they can be mitigated. Now, in this presentation, we'll take a look at some considerations for implementing storage both locally and in the cloud. And like any comparison, there are always pros and cons, but beginning with local storage, one of the main benefits is, of course, speed. Storing data locally is quite simply faster than uploading to the cloud, particularly if you are dealing with a lot of data on a regular basis. Even simple storage mechanisms such as internal storage on a server is going to be faster than continually uploading. Of course, security and control is a major concern. When it's local, you have full control of backups. You have better overall control of who can access the data. And in the case of external storage, you can disconnect the drives. You can keep the data safe from attacks. Any kind of attack coming from the outside, regardless of the skill of the attacker, will not be able to reach a physically disconnected storage medium. So, you have those options. You can decide for yourself what kind of security you want to implement. Now, there are, of course, considerations with local storage. It can absolutely be tremendously expensive when you start getting up into the highest levels of SAN storage. So you have to create and maintain some kind of local storage system. You need the hardware, you need the software to manage and maintain it, so that can be very expensive. You also have to consider on-site disasters, which of course can destroy the data. So to mitigate that risk, you typically have to implement off-site storage, which translates into more administrative overhead. So there are always considerations. There are always pros and cons. So if you then look at cloud storage, on the plus side, it is absolutely very cost effective. There is minimal maintenance because all of that infrastructure, for example, a SAN, is not required at all. Scalability is absolutely there. You can increase or decrease the storage however you see fit. So it's not always just scaling up. In many cases, you can scale back. Disaster recovery is effectively already addressed. You can secure the data remotely, and you know it will remain safe. You have that off-site storage simply by nature because it is at the cloud data center, plus very likely a local copy. But even the cloud data centers themselves usually will replicate that data to other data centers. So you always have multiple copies. And you certainly have the accessibility. You can access the data from any device with an internet connection. So typically the data that you tend to find in cloud storage is something like a database that drives an application, so that when I open my application, it doesn't matter where I am, it doesn't matter what I'm using. As long as I have an internet connection, the application can access the data. But of course, there are the downsides. The speed. It requires a good internet connection. For example, if there is a lot of data to back up, it could absolutely take a long time without a good connection. And perhaps the biggest issue is control. There is always sensitive data, so you need to know, is it even acceptable for it to be stored anywhere other than within your own organization? And if it is acceptable, then you need to understand what the risks are and how you can mitigate them with respect to keeping that data sensitive. So, as mentioned, there are always considerations. There are always pros and cons, and it might depend, of course, on the application, what it is that you need to do, and where that data really is best suited to reside. But you do have those options, and in many cases, it's possible that you can implement a mix of both. You might have local data that is entirely appropriate to be local, and then you have data that should be in the cloud. So there's nothing wrong with that either. You don't have to make the call where it's all or nothing. It's dependent on what your needs are. And as mentioned, you can always decide for yourself where the data should best reside. All right, for our exercise this time, we'll ask you to describe the types of cloud services available, then to describe the various cloud delivery models, and finally to describe local versus cloud storage considerations. So what we'd like you to do is take a few minutes, pause the recording, jot down some responses, and then we'll come back in a few minutes to review, and we'll see how you made out. So we'll see you shortly. All right, our first task was to describe the types of cloud services available, and these include software as a service, platform as a service, and infrastructure as a service. Now, that said, when you create any kind of cloud subscription, you don't really specify that I am subscribing to SaaS or PaaS or IaaS. It is simply something that is available, if you will. For example, if you are only creating virtual machines, that is at the IaaS level. If you then need some development environment created, well, you can implement those resources, and that resides at the PaaS level. If you only need software, that of course is at the SaaS level. So you don't choose these levels per se. They are just categorizations of where you can find the appropriate types of resources, and you can choose any type at any level. Then we asked about describing the various cloud delivery models. This includes the public cloud, the private cloud, the hybrid, and the community cloud. And again, it all depends on your particular implementation, what you need, what you have, where you are going. All of those need to be considered when it comes to choosing the appropriate delivery model. Then finally, we asked about the difference between local versus cloud storage in terms of some of the considerations. And again, recall that local storage is certainly faster with greater control, but can be expensive and certainly more administrative overhead, whereas cloud storage is very cost-effective, scalable, and accessible, but not as fast, less control, and certainly some security and privacy concerns. So hopefully you made out okay with those exercises, and if so, we are ready to move on. Now, in this presentation, we'll take a look at the Domain Name System, or DNS, which is quite possibly the most heavily utilized network service on the internet. And even if you aren't familiar with this, and even if you are brand new to networking, you have undoubtedly interacted with this service countless times. Because if you have ever gone onto the internet with any type of device to access any kind of website, you have used the DNS service. So it is primarily made up of DNS servers, which for all intents and purposes maintain a phone book of the internet. They have a directory of domain names, and those names are then translated to IP addresses. Now, this exists because, as you can see in the graphic, we use names, domain names specifically, to access websites, www.brocadero.com in this case. But any two systems that are communicating with each other using TCP/IP need to know each other's IP address. So when we specify www.brocadero.com, that does not include an IP address, so it is quite meaningless to the computers. They need that IP address. So this is essentially the main job of DNS, to translate that name to an IP address, just like a phone book translates a person's name to their phone number. And this exists quite simply because, as human beings, we remember names much more easily than IP addresses. Again, the example, www.brocadero.com. It's easier to remember that than 131.50.67.90. And even if you think, well, that number's not really all that hard to remember, that's fine. But we are talking about every IP address on the internet. So there would never be any way that you could remember the IP addresses of all the sites that you want to access. And even then you might think, well, I don't even know the names, I just search. Well, that's fine too, but the search results would be quite meaningless if they pulled back nothing more than a bunch of IP addresses. We see descriptions, we see domain names underneath the description. So again, we just click on the link because we recognize the names. From that point, it still has to be translated to an IP address. So again, ultimately, the IP address must be known for communications to occur. We use various means to find the internet resources we want, but we almost never specify the actual IP address. Now, DNS consists of a distributed hierarchical database stored on separate DNS servers on all networks that connect to the internet. Now, in an upcoming presentation, we'll talk about two different types of DNS, internal versus external. So for the time being, we are referring to the internet, which is external. But the idea of it being distributed means that it is not all on one server. And that would just be entirely impractical if there was a single server that had to handle all of those name resolution records for the entire internet. It would just never work. It might be able to handle the number of records Large-scale databases can handle hundreds of millions of records, but it's the process of resolving those requests. When a client says, here's a name, find the IP address for me, that would never be able to be handled by a single server. So we see multiple servers that have just portions of the database stored on it. And then it's also broken down into this hierarchy, levels. And the name that you see there, www.brocadero.com, does indicate those levels. Now, we'll talk about that in greater detail later, but the www actually refers to a specific host. Brocadero refers to the organization, and of course there could be multiple hosts within that organization. .com refers to a higher level, where of course there are many organizations within that level, but that's the idea of a hierarchy. As you move through the hierarchy, you go from level to level to level, and you ultimately arrive at the destination. So again, we'll talk about that hierarchy in greater detail later on. So the DNS servers store, maintain, and update parts of the database for which they have authority, and consult them when responding to requests to resolve the specified host names into IP addresses. In simpler terms, that means, again, that if you are the administrator of Brocadero.com and you want to have a publicly available website, then you have to register that site, and you have to inform the public internet, for lack of a better description, that this is the DNS server responsible for resolving all names within Brocadero.com. Again, maybe your web server, your mail server, your FTP server, an application server that might be available. It doesn't matter, but you can have as many addresses as you want that might be available to the public internet, but it's up to you. You manage it. So you create what's known as an authoritative DNS server, and it's your job to make sure that server responds to the requests coming in from the internet and says, here you go. Here is the address for that system. And since I'm the authoritative system, do not listen to anyone else. So if somebody tries to say, well, here's a different record, they simply will not listen to it because they are not publicly registered as the authoritative server. So again, that's how you break the internet down into these smaller portions, and you define who is responsible for which portion. Earlier, we discussed some of the basics of DNS. So in this presentation, we'll take a closer look at the structure and the hierarchical nature of the database, as well as comparing internal to external DNS. And these are the two implementations I touched on earlier as well. But internal means that all of the members that are participating are likely part of an internal domain. Now, that doesn't really describe a whole lot, but let's hold that thought for a moment. So when any system is requesting a name resolution to an IP address, it will use a local DNS server for any DNS name resolution tasks. So what does this look like? This is you at work, in your office, interacting with the servers that you need to contact on a daily basis to do your job. You submit print jobs, you copy files from servers, you retrieve your email. But all of those servers are all within the internal organization. So none of this ever touches the public internet. And the IP addresses that you would be getting back from the DNS server would almost always be a private IP address. So print serve 1 is 10.0.50.5, something along those lines. That's a private IP address. So the applications that you use typically still involve submitting names because you still might not know the IP addresses. So your internal DNS servers are still responsible for translating that name into an IP address. But again, none of it ever leaves your environment. It's all behind your router or your firewall. So external is effectively the exact opposite. The members that are participating likely belong to a different domain other than your own. So you will use an internet DNS server to obtain any information about the network. So what does this look like? This is still you at your office, but now you are trying to get to a website that is any other site other than your own. So some other company, for example, or just any site, it doesn't matter. Your DNS server within your own local environment is not responsible for resolving the name of somebody else's server. So it forwards the request out onto the public internet, and it will use either the DNS server of the other side, whoever that might be, or it might use something like a hosted DNS server, and we'll see that in a moment. But again, the idea is it's any kind of name resolution request for a system that is not in your network. So with respect to that internet DNS server, what does that refer to? Well, again, every little environment, every portion of the internet has to have a DNS server somewhere that is responsible for resolving the name requests. And that can be your own server. In other words, if you have an internet presence within your organization, then there does need to be a DNS server that is publicly available to handle the name resolution requests, such as your website. So you can implement a publicly available internet-based DNS server within your own environment, but it would not be the same DNS server as the one you use internally. In other words, you submit a print job, it is your internal DNS server that resolves that name. When someone from the outside wants to get to your website, they still have to find a DNS server, but it would not be the same one. Typically, this would look like a web server and any other server that needs to be publicly available in a demilitarized zone, a perimeter network that is separated from your internal network by a firewall. Also out there in the perimeter network is the publicly available DNS server for that website. So that's the one that handles the name resolution requests for your website. But everything you do on the inside is handled by the internal DNS servers, and those two servers do not talk to each other. Because if you only had one to handle everything, the internal and the external, you would have to expose all of your internal IP addresses to the public internet, and that leaves you wide open for attack. So you have two completely separate and separated by a firewall DNS servers. But that can introduce some problems because let's say you are a small to medium-sized organization and you do set this up exactly like that, a web server and a DNS server in a demilitarized zone, and it's working fine. But if that DNS server goes down, you lose your entire internet presence because no one is resolving the name requests for the people trying to get to your web server. So these mystical internet DNS servers often are third-party DNS servers or cloud-hosted. These offer several improvements such as speed, reliability, parental controls, phishing protection, and you can see improved scalability, reliability, and availability with cloud providers. So this is you simply saying, I need an internet presence, but I don't want to handle the DNS. So you subscribe to the service of someone else. Web providers, web hosting companies offer these services. Many internet service providers offer these services as well. And they have, in a lot of cases, more resources to dedicate to this service. So this is where you get the better speed, reliability, control, things along those lines. So it's up to you. You can implement your own DNS both internally and externally, but often these third-party providers might do a better and or a more reliable job. So then looking at the hierarchy, it's comprised of the following elements: the root level, often known as the dot portion of the domain. And in fact, when you enter a domain name into a browser, such as www.brocadero.com, it's actually www.brocadero.com . It ends with the dot. It's just not displayed. But this represents where you start looking. You have to start somewhere. So DNS servers are programmed with addresses for root servers so that your DNS server in your environment, if it's looking for a web-based name and it doesn't know where to start looking, it starts at the root domain. The root servers only need to know about the next level down, the top level domains, .com, .ca, .gov, .edu, .org, the extensions we're all familiar with. So it forwards the request to the appropriate top level domain. And if I'm looking for brocadero.com, in this case it would send it to a .com server. One of the .com servers would have a publicly registered entry for Brocadero. If I want to, within Brocadero, if that's my organization, I can subdivide it into something like East and West, or sales and marketing, or anything along those lines. Now that's your call. You don't have to do that. And then finally, at the most specific level, we have the host. So www actually refers to the web server. Mailserve1 would refer to the mail server, and that might be in one of the subdomains, but it doesn't really matter where it is. That's where you get to the actual specific host system. So each level of the hierarchy only needs to know about the next level down, and that's how you ultimately find the appropriate system. Now, that being said, there are also two different types of zones, forward and reverse. And it's quite simply the direction. A forward, by far the most common, simply converts names to IP addresses. This is commonly used for websites, and it's pretty much what we use every day. The opposite is the reverse zone, and this simply does the same thing in reverse. It converts an IP address into a domain name. So in other words, it's the scenario where you actually know the address and might not know the name. So commonly used in network troubleshooting to determine if this particular IP address is being converted to the correct name. So again, those are some of the basic characteristics of the DNS service, and as mentioned earlier, perhaps one of the most important networking services of the internet. In this presentation, we'll take a look at the SOA, or Start of Authority record in DNS. This defines general parameters for the DNS zone, including, and perhaps most importantly, the identity of the authoritative server for the zone. Now, each zone contains a single SOA record, which specifies a single server as the authoritative server. So, particularly for internet DNS names, the process is, I want to register www.mycompany.com. I have to go to a public registration company and say, here's the name, and I must then specify a DNS server somewhere. It can be my own, or it could be through a provider of some kind, or even the public registrant themselves. But a server somewhere has to be marked as authoritative for that domain name. Once that is all done, once it checks out, if you will, then it is marked as authoritative, and this prevents anyone else from just coming along and creating another zone and saying, no, I'm authoritative, because there can only be one SOA record with one authoritative server. So once yours is publicly registered, no one else can also be authoritative for that zone. So other public DNS servers will only ever forward name resolution requests for that domain name to the authoritative server. So again, it protects your zone and prevents someone else from quite literally stealing your DNS name. Now, you can search for more about SOA records in RFC 1035. It just discusses the implementation and the specifications for domain names and how SOA records work. But they have various properties within the record that define everything you see here, the current zone. for which this server is authoritative, a class, which is typically IN for internet. We'll see that a little bit later. The type of record, which in this case is quite literally the SOA record. It specifies this is the record designating this server as authoritative and all of these other properties as authoritative. The primary master is the server itself, so the IP address, a contact email if somebody wants to contact you about that domain name, a serial number, which is used for if you are replicating the zone information to other servers for redundancy. This ensures uniqueness and that no conflicts ever occur. A refresh time for when clients should simply refresh the values to ensure they are correct. A retry time, if they are unable to connect, they should continue to retry for this amount of time. An expiration time, which is generally for the entire registration itself. So if, for example, you registered for 2 years, that would be the expiration. And the TTL, or time to live, is how long that specific resolution request is valid for. So it is possible that the IP address might change, for example. So you can set a TTL really at any value you want, but it does mark a validity period for this name equaling that IP address. So again, should the address change, the TTL should be updated. But in essence, they just define those overall properties for the zone. But again, the key component is the fact that it ensures the uniqueness of the name and prevents someone else from trying to become authoritative for your DNS zone.
Now in this presentation, we'll take a look at some of the other types of DNS records, beginning with NS, or name server records. These list the name servers for the domain and allow other name servers in other domains to locate names in your domain. So these are used when you have more than one name server in your zone. And that's especially common in large zones, because if you only had a single name server, for example, the authoritative name server, then it would be responsible for handling all name resolution requests, which might simply overwhelm the server. Plus, it would be a single point of failure. If it went down, the entire zone would be inaccessible. So you can have as many other name servers as you want to spread the load and increase the fault tolerance of your zone. So when you create the records, the name is the domain that will be serviced by this name server. The address class is IN for internet. The record type is NS for name server. And the name server name sounds a little redundant, but it is the name of the name server. So the fully qualified domain name of the server responsible for the domain. The A record makes up the bulk of almost every DNS zone database. A simply stands for address, and they're often referred to as host records. They are certainly the most basic type of DNS record because it is quite simply the mapping of host name to IP address. And if it's IPv4, the A record resolves a 32-bit address. But if you're using IPv6, then there is a AAAA record to resolve those. And they simply have 4 A's because 32 times 4 is 128. But if you're using both records, both protocols, you actually need both the A record and the quadruple A record. The inverse of the A record is the PTR, or pointer record. These are stored in reverse lookup zones so that a DNS name can be retrieved from a known IP address. This is sometimes used to validate that the source of a trusted domain's communication, such as email, is coming from the correct IP address for that domain. The mail exchanger record, or MX record, is used to specify servers that are configured to accept mail on behalf of the domain. So when you send any email, for example, to any given domain, there has to be an MX record that indicates this is the mail server that will accept that mail and process it. So the parameters include the mail server itself and a preference, which is used to specify a server when there's more than one MX record present. So you can see an example here, the domain it services, IN for internet, MX as the mail exchanger. And again, if there is a preference, you could specify mail server 1 as the preferred server. SRV records are service locator records. They enable clients to query DNS servers for the location of servers providing a specific service, such as a domain controller, because they provide the ability to log on. So it enables more efficient management and distribution of logon traffic, particularly in larger networks. Now, that's only one example, but the idea is that it's certainly fine to have the name and address resolved, but in many cases, you need to know as well, what can the server do for me? What type of services does it provide? And logging on is just a perfect example. This allows the clients to say, well, who are the logon servers? It's not just the IP address I need this particular type of service, this particular type of request handled. Which servers handle those types of requests? And DNS can actually send back that information in the form of SRV records. So there are 7 pieces of information in an SRV record. The domain name, the domain for which this record is valid, which incorporates a service name such as LDAP, Lightweight Directory Access Protocol, over TCP in Brocadero.com in this example. Its time to live, 86,400 seconds is 1 week. The class, this field is always IN for internet. The record type is simply SRV. Priority and weight are similar, but priority specifies a preference. But if you have a lot of servers, there might be some with the same preference. So if equal priority is specified, then it considers weight. So let's say you had 5 servers that all had a priority of 3. Within those 5 servers, it would then look at the weight. And if the weight is the same, you're basically saying any one of those 5 is fine. You can kind of round robin the request if you wanted to by specifying a weight of 100, 200, 300, 400, so on. The port number is the port where that server is listening for that service. In the example of LDAP, it's port 389. And the target is the fully qualified domain name of the host computer, dc1.brocadero.com, for example. Now, the TXT, or text record, is used to provide additional information about a named service. And one common example is an SPF, or Sender Policy Framework Network. This is the type of text record used to identify mail servers that are permitted to send mail on behalf of any given domain. This is effectively used to prevent spammers. So I can explicitly say, this mail server is permitted to send mail on behalf of our domain, so that it is not identified as a spammer. You might also see a DKIM, or Domain Keys Identified Mail, which is also used to validate the organization delivering email. It's not uncommon that sometimes you need to send mail through someone else. And in that case, you're basically saying that this server in a different domain is actually allowed to send mail through this other organization. They might be a provider of some kind or a partner organization, things along those lines. So these validate that the server is allowed to do so. Finally, a CNAME is a canonical name, also referred to as an alias record. This is used to point one domain or subdomain to a different host name where an A record already exists. Quite simply, it's an alternative name for any other existing A record. And it doesn't necessarily have to be from one domain to another or a subdomain to a parent domain. Even within the same domain, you might simply want more than one name for the same address. So for example, you might have a web server and it might be listed as www.mycompany.com. So its host name is www, but it might also provide the FTP service and it's the same server. So you want people to access the FTP service by ftp.mycompany.com. So same server, but we need 2 different names. So you would create a canonical name for the other type of service. So you can create as many nicknames, if you will, as you want for any given server. So those are just some of the different types of records you'll encounter as you start creating your DNS zone database.
In this presentation, we'll take a closer look at DHCP, or the Dynamic Host Configuration Protocol. This was implemented to replace manual assignments, particularly in very large environments, If you had thousands of clients, it would take a very long time to manually configure each one. Plus, you're much more vulnerable to simple typos and mistakes. So this is used to automatically configure the IP address, the address of the default gateway, the subnet mask you are using, and various other options, most commonly the DNS servers that you are using. And this has become the preferred method for dynamic assignment of IP addresses, as long as the scope or the pool of addresses on the server is configured correctly. Then you can rest assured that the clients are getting a valid IP configuration free of errors. So the process is that a client is configured to obtain an IP address automatically, and for Windows systems this is the default. In the properties of TCP/IP, it is set to obtain an IP address automatically. So when the client boots up and realizes this, it sends out a DHCP discover packet. This is a broadcast that is used to locate DHCP servers on the network. And it has to be a broadcast because you don't yet have an address. So you initialize a basic form of TCP/IP that is only capable of broadcasting. Now, since broadcasts are heard by everyone, the DHCP server will hear it. But if for some reason you cannot reach the DHCP server, just because of general network issues or the server going down, then the client will assign itself an automatic private IP version 4 address, or APIPA, in the event that it does not get a response. Recall, APIPA assigns a 169.254.something.something address. So it's not particularly useful in terms of communicating, but it is useful in diagnostics. Once you see that address, you know that there is a problem communicating with the DHCP server. Then you can begin troubleshooting. So, assuming that the server does hear the request, then it will send back a DHCP offer. So, it offers up an address with the lease information to the client, basically saying, here are the properties of this configuration, how long it's valid for, and various other configuration options. But this is also a broadcast because, again, the client does not yet have an IP address. Since the original message was a broadcast, not only will this particular DHCP server send out an offer, but all DHCP servers will send out offers. You may have more than one. So when a client receives an offer, it can accept it by again broadcasting the DHCP request. So it says, I like this one. I like that lease. That's the one I want to use. So again, in the event that there are multiple DHCP servers, the client will typically accept the first one it received, at which point the other servers will withdraw their offers. So things start to quiet down a little bit, but these are still broadcasts because you still do not have the IP address yet. Finally, the DHCP server will send out a DHCP ACK, or acknowledgement. This is the server saying, all right, you may have that address, and it includes the lease duration and other details, but basically this is the server saying everything checked out. You may now start using that address. Once you receive the acknowledgement, now you have the IP address. You can bind it to your adapter and you can stop broadcasting. Now, there are a few other types of messages. The DHCP NAC is a negative acknowledgement, and this is issued when the address requested by the client cannot be used. For example, it's already in use. Perhaps some other DHCP server already assigned that address. So we can't configure a conflict in addresses, so you'll get a negative acknowledgement. A DHCP decline is issued when a client determines that there's something in the configuration that is invalid. Maybe the subnet mask is not right, something along those lines. So the client will simply say, no, I don't want that one. And then you might also see a DHCP release message, which is issued by the DHCP client to release the IP version 4 address and effectively cancel any remaining leases. That is also something that is commonly used in troubleshooting. If you cannot communicate, you can simply discard your configuration, then request a new one by performing an ipconfig/release, then ipconfig/renew. That basically just requests a new configuration. And if you get a different address, for example, and then everything starts to work, you can assume that there was something wrong with the previous configuration. So again, the whole idea is to effectively assign all of your clients in an automatic fashion so that you do not have to go from system to system manually configuring these values. And again, you can ensure that as long as the scope is correct, that your client configuration will be correct as well. But from time to time, there can be issues, so some of those other types of messages may be encountered when you are examining things like the Windows event log. You might see some of those different types of messages from time to time when troubleshooting. In this presentation, we'll take a look at NTP, or the Network Time Protocol. And this is a hierarchical protocol that is divided into what's known as stratum levels, which allow you to define a distance from a reference clock. Now, I'll come back to that structure in a moment, but the reason why this protocol exists is because there are a number of network functions that are time dependent, or at least time sensitive. And one common example is when you log in. If you are in a Windows environment in particular running Active Directory, there are servers known as domain controllers which process the login requests. They use a protocol known as Kerberos to handle the authentications, and provided you supply valid credentials, you are issued what's known as a Kerberos ticket. And this is like a little security badge that you use to show whenever you need to access a resource. So if, for example, you simply want to get to a file on a file server, the file server will say, hold on, show me your ticket. So if the server that issued you the ticket and the file server don't agree on what time it is, there can be problems, because the Kerberos ticket has a timestamp that says when it was issued and how long it is valid for. They aren't valid indefinitely. If you just get up and walk away from your computer, for example, after logging on, and your computer does not go to sleep, the session will ultimately time out so that someone else doesn't come along and use your system to access resources. So let's imagine you are approaching the timeout period. If you try to access that file, and again, the two servers do not agree on what time it is, then the file server might say, hold on a second, that ticket has already expired, even though from the perspective of the domain controller, it has not. So you could end up with these problems with respect to that disagreement in time. So that's where the levels come into play, and stratum 0 is, of course, the highest level and represents the clocks themselves. And typically these are exceptionally accurate devices such as atomic clocks or GPS clocks, but these aren't standard networking devices, and we don't have atomic clocks in our LAN environment. So we don't have standard network connections to these devices, so they're used as the reference clock, the synchronization source. Everything begins there, but the systems that are in stratum 1 would have proprietary interfaces to those clocks. Now that they have synchronized by those clocks, they can act as the source for the next level down. So in stratum 1, we do see now the most accurate NTP time sources that are accessible by standard network connections. So stratum 1 devices are typically synchronized by the stratum 0 reference clock, but once they have been given the time, they will handle the distribution of that information to the servers in the lower levels. Now, each one can synchronize with the source itself, but you'll also see there are some horizontal arrows, which means that they can also poll each other to say, well, I got time X. Did you get time X? In other words, they can compare and they can adjust for any kind of lag or offset or latency in the communication itself. So Stratum 2, in essence, then just does the same thing as 1 does with respect to 0. So as far as 2 is concerned, 1 is the highest level. So they are synchronized from Stratum 1 using standard network connections. Now, they might not be as accurate as Stratum 1 servers because there can be delays and effectively jitter in network communications. But this, of course, is why they are able to poll each other. Plus, they can also take into account how far they are from the original source, because there is some kind of delay in all network communications. They can actually accommodate for that delay. So if the server says it's time X, but we know that the packet took, let's say, time interval of Y to reach us, well, then we can calculate what the actual value was in terms of the original source value. And then finally, in Stratum 3, these computers are synchronized by way of Stratum 2 servers, and they employ the same algorithms used in Stratum 2, and they can in turn act as servers for Stratum 4 computers. So in other words, this hierarchy can just keep going and going, but like anything in a hierarchy, ideally you want it to be as simple as possible, because the farther away you get from the original source, the more likely you are to encounter skew with respect to the actual time. So again, in a standard LAN environment, we don't have access to the GPS and the atomic clocks. Typically, your domain controllers are set to subscribe to a Microsoft time service. That time service would be Stratum 1. So again, we don't have direct access to those atomic clocks. We have access to internet-based services that reside at Stratum 1. Then your domain controllers would effectively be Stratum 2. They then can be the synchronization source for all other servers and all other clients in your environment, which would effectively represent Stratum 3. And pretty much that's where it tends to stop, so that again, we don't just keep going and going and going and increasing the likelihood of that skew. So once that has been implemented, all of the systems in your environment will effectively agree on what time it is. In this presentation, we'll introduce the three basic categories of cloud services: SaaS, or Software as a Service, PaaS, or Platform as a Service, and IaaS, or Infrastructure as a Service. So beginning with SaaS, this is a software distribution model whereby you have a third-party provider of some kind, and they effectively host the application for you. That application is then made available to customers over the internet. Now, we typically aren't talking about desktop level applications such as word processors or spreadsheets, but rather larger scale multi-user applications such as enterprise resource planning or customer management software, or maybe anything that is driven by a database. So again, the idea is that everything is available as a service. The reason why you see that AAS after all of them is because there is a lot of infrastructure required to provide these services. So the basic idea is that rather than you investing in that infrastructure yourself, you simply subscribe to those who already have it. If you needed to implement a large-scale CRM application in your own environment, you would, of course, have to invest in the servers, the storage, the networking, the software itself, the licensing, then the deployment, the configuration, the management, the upkeep. All of that has to be in place for you to effectively use that application. That's all well and good, but again, these providers already have all of that. So you simply subscribe to it. You get a portion, if you will, or a section of that application that you can use. And now you don't have to invest in any of that infrastructure. It's already there. And again, when it comes to cloud services, this is applicable to all cloud services. You only pay for what you use. So if you were a smaller environment and you needed to support, let's say, only maybe a few dozen users in a CRM application, then you would only pay for that amount. If you were a much larger organization and you had to support hundreds of users, of course, you would pay more. But in both cases, you still don't have to invest in the infrastructure. It's already there, so you just subscribe to it. Everything is effectively a pay-as-you-go model. So in terms of advantages, the time to deployment is very rapid. You don't have to acquire all of that hardware and software and licensing. It's already there, so you really can get started almost immediately. Greatly easing the administration as well, because again, all of that infrastructure that needed to be implemented in the on-premise environment is just gone. So you don't have to look after the servers themselves or the network configuration or anything along the lines of licensing. All of that goes away. It is highly scalable because, again, the providers have tremendous amounts of resources available. It is very accessible. It only requires internet access and a browser. And again, because of the degree of robustness, if you will, at the provider, it is very resilient. They have redundancy built in to just about every aspect of every service, so it's very fault tolerant. And of course, there are disadvantages: security, the privacy of sensitive information, and the compliance, the location of the data are typically foremost in the concerns of users. Quite simply, the data itself is not under your physical control, and really you don't even know where it actually resides. Plus, in most cases, you are sharing the storage of that data. So if I do subscribe to my CRM application, my little portion of it is kept separate from any other given client, but it is still possibly available to the people who manage the environment itself where the data actually resides. So the privacy is a concern, and again, the fact that it is physically not under your control can be quite limiting. Performance can also be an issue because you are ultimately using the internet to access that application, so that of course can cause problems. Now, PaaS, or Platform as a Service, is a model used typically to develop and deliver applications over the internet. It delivers software tools and development environments to users, again, as a service. And this really is the same type of scenario whereby if you want to create your own development environment in-house, you still need the servers, you still need the networking configuration, you still need the software for the development environment. So all of that can be made available within your cloud subscription as well. And then ultimately, you do not have to invest in all of that infrastructure. Again, there are tremendous advantages. For testing and deployment, you can easily test different configurations. You can create virtual machines in any configuration that you want to ensure that your application will run across multiple different operating systems, for example. And you can very quickly add new features to an application. So this dynamic allocation is very easy to implement. There is improved support and minimal management, again, because there is just so much less in terms of the infrastructure within your own environment. Again, there are disadvantages. That lack of control is always a concern. It is typically a shared platform. All of the other subscribers are using the same ultimate environment as you are, so data security still remains a concern when it comes to the privacy and the retention of data. And then finally, infrastructure as a service, or IaaS, provides things like virtual machines, the operating system itself, the networking capabilities, and the security. So getting close to the hardware level, but this is the lowest level of service. So if you need more servers in your environment, for example, you can just create new virtual machines and they can come with any operating system that you want in many cases. Advantages here, cost savings. Again, that lower infrastructure costs. You don't need the physical systems to host the virtual machines. They are already there at the provider. Again, highly scalable. You can quickly scale up or down depending on the requirements, and highly available as well. It is really up to the provider to ensure that the redundancy is there for all of these features. Again, disadvantages. Maintenance may not be included. Now, that depends on how you approach this, if you will. But with respect to things like versioning and upgrades, that is usually up to you. But if we just think about a virtual machine, for example, all you see is the virtual machine. You can manage it however you want. So let's imagine you create a virtual machine with a particular version of Windows Server. The versioning and the upgrades and the updates for that server are up to you to manage. But the underlying hardware is up to the provider. So that's why I say maintenance may not be included. It depends on what you are talking about. But keeping the hardware current and upgraded and up to date, that is absolutely up to the provider. Again, security may not be adequate depending on the requirements, and there are always legal considerations, typically depending on where data actually resides. But ultimately, you can subscribe to any or all of these levels of service depending on what you need. Now, in this presentation, we'll take a look at IPAM, or IP Address Management. And this is a service that provides IP version 4 and 6 address infrastructure administration and monitoring. Now, that's actually a key word, the infrastructure, and I'll clarify that in a moment. But what it is you are managing are your DHCP and or DNS servers themselves. So it offers enhanced IP address management. Effectively, all subnets that are managed by all servers can be managed by IPAM. So that's what I meant when I said infrastructure is the key word here. A lot of people tend to ask me, well, what is the difference between IPAM and DHCP? They are both for managing IP addresses. Well, for starters, we see that DNS is also incorporated into the mix here. So that's one of the basic differences. But this isn't managing the clients like DHCP is. This is managing the servers. Your DHCP server is responsible for handing out the IP addresses to the client systems. That's its job. That's all well and good, but in larger environments, you might have dozens upon dozens of DHCP servers and dozens upon dozens of DNS servers. That in and of itself then becomes fairly complex to manage. You would have to go from server to server to server, or at least connect remotely to each one to see what they are all up to. IPAM allows you to manage those infrastructure servers, the DHCP servers and the DNS servers, from a centralized location so that I can see what all of my DHCP and DNS servers are doing within my environment. So it's a complete integrated management of your IP address spaces, both dynamic and static. I can see which systems are statically assigned. I can see which ones are dynamically assigned, and I can create these customizable inventory views of the entire IP address space. I can monitor both versions in terms of the address utilization, so I can see that this server has issued out this many addresses, and I can configure these usage alerts and notifications with respect to thresholds. Once a particular server reaches 90% of its available address space exhausted, then I can ensure maybe that another server takes over and effectively balances and distributes the load a little more effectively, so that I don't have one server that's being heavily utilized and another one that's being entirely underutilized. It's a complete multi-server management environment. And again, that's the idea. You are managing the servers, not the clients. You can discover DNS and DHCP servers across an Active Directory forest. So again, in very large environments, I can find out all of the servers performing these services. And it offers configuration support of each DHCP server and or scope. So I can not only monitor these servers, but I can actually get in and configure the servers. So you can, to a degree, still support your clients. Now, it's generally not meant to do that, but you absolutely can. It supports simultaneous updates for common settings across DHCP scopes and DHCP servers, so that if there is some kind of setting, such as the DNS servers, that are consistent across these 5 servers, I can ensure that they are consistent. I can monitor the scope utilization, again, keep an eye on how many addresses have been issued by any given server, and I can monitor the availability of those servers as well. If one of them goes down, for example, I can be alerted, and there is manual addition or removal of the managed servers. So if I have some DHCP and or DNS servers that should not be managed by IPAM, I can remove them. Maybe there's an isolated group of servers that are handled by specific people. That's fine. You can add servers in. You can take servers out at any time. It also supports network audit functions. You can query the event catalog for DHCP configuration changes using a single console, so I can see who is doing what with respect to any kind of change. I can create advanced queries to track users, devices, and IP addresses at specified interval times as well, so I can have regular updates, if you will. I can export the audit findings to create reports, and I can resolve any kind of configuration problems a little more easily because, again, all of this is accessible from a centralized interface. I don't have to run around to all my different servers to see what they are up to. Now, it also supports role-based access control. I can use this to customize the types of operations and access permissions with respect to the specific objects in IPAM. There are standard groups, a local IPAM security group, a built-in IPAM role-based access group, and a custom IPAM role-based access group. Simply meaning, like all other role-based access groups, I define the permissions on the group, and then I simply determine which users should be in those groups. So I can create these local ones that would be for just that server only, or use the built-in and custom to create larger groups that can manage multiple servers. It's entirely up to you, but it's always the same approach when it comes to role-based access control. Determine who is able to do what, over what kind of scope of servers, place them into the appropriate roles, manage the permissions of the roles. And finally, you can also manage your virtual address space using IPAM. This enables the same functions and capabilities for a virtual IP address infrastructure as a standard physical IP address space does in terms of managing those servers. And again, recall that virtual address spaces are typically implemented for things like clusters, server farms for perhaps web servers, load balancers, any kind of virtual machine networks that you create using something like Virtual Machine Manager, things along those lines that basically just don't have a single physical interface dedicated to any particular address. Point being, you can manage your entire address space, whether it's physical or virtual, using IPAM, and it's typically implemented again in the larger environments where there are multiple servers handling those services. If you only had a single DHCP server and a single DNS server, that's not all that much to manage. So overlaying IPAM in that case might not really be much of a benefit. You can certainly still do so, but it's typically meant to be implemented in the larger environments where we have, again, usually dozens of servers performing those tasks. So we can basically just get this higher level overview of the entire environment and how our IP infrastructure is being implemented and utilized. Now, for our exercise this time, we'll ask you to describe how the DNS service works, then to describe the different types of DNS records, then to describe how the DHCP service works, and finally to list some of the features of IPAM. So as per usual, what we'd like you to do is to take a few minutes, pause the recording, jot down some responses, and then we'll come back to review and we'll see how you made out. So we'll see you shortly. All right, our first task was to describe how DNS works, and just at a basic level, the DNS servers maintain a database of IP address to host name mappings to resolve client queries. We, as users, like to refer to systems by using a name, but the TCP/IP protocol requires an IP address. So we query the DNS server and we say, here is the name. Please find the associated IP address. The DNS server will check the database, and if the listing is there, it will send back the IP address. And even if it's not there, it can possibly query other DNS servers to find it. So ultimately, we can communicate using names instead of having to remember IP addresses. Then we asked about the different types of DNS records, and there were several. Beginning with the SOA, this is the start of authority, and this designates this particular DNS server as the authoritative server for this namespace. And this prevents other servers from being able to usurp your name. So you are responsible for handling all name resolution requests within that domain. Once you have that, you can establish additional NS or name server records to simply distribute the load. There are several other servers that can perform name resolution requests. They are the name servers. The A or the address records are also known as the host records, and they are by far the bulk of virtually every DNS database. They are simply the mappings. This address is assigned to this host. And the 4A record is the same thing for an IP version 6 host. The MX record is your mail exchanger, the server that is designated to accept mail for your domain. SRV are service locator records, so not only can I resolve a name to an IP address, but I can find out which services this particular server can supply for me. Text records are typically used to implement which mail servers are valid so that I can try to reduce spamming, for example. And CNAME is a canonical name or an alias, just the ability to give any other host a different name. Then we asked about the DHCP service, and for this, servers maintain a pool or a scope of available IP addresses that they can lease to clients. So clients boot up and request an IP address. The server hears this request and says, here you go. You can use this IP address. The client says, thank you very much. And in essence, we'll start using that address for a certain amount of time so that you don't have to manually go around from system to system to system, manually configuring each client. And finally, IPAM is the management of the DHCP and or DNS servers from a centralized console. In larger environments in particular, you might have dozens upon dozens of DHCP and or DNS servers, and that can introduce a lot of overhead in terms of administration. IPAM allows you to collectively administer all of those servers to just try to reduce the overall administration required to maintain such a large environment. So hopefully you made out okay with those questions, and if so, we are ready to move on. Now, in this presentation, we'll take a look at some of the physical media types or cables used in network implementations. Beginning with coaxial, this consists of a central metal core made of copper that is then surrounded by an insulator and a braided metal shielding to help reduce electromagnetic interference, and then an outside cover known as a sheath or a jacket. Now, in terms of network implementation, coaxial cable is virtually extinct. It was used back in some of the early implementations of linear buses and came in two varieties nicknamed thicknet and thinnet, quite literally due to the thickness of the cable. Thicknet had a better quality signal and can travel a bit farther, but it was more expensive and a little more difficult to implement. Thinnet, not quite as good in terms of quality and didn't travel as far, but it was less expensive and easier to implement. But again, these days I can't imagine you would ever find an existing implementation of coaxial cable for LAN implementations. So the next type then is what's known as UTP, or unshielded twisted pair. And this is where we start to see what you might think of as regular Ethernet cable. But with unshielded twisted pair, we do have these multiple pairs of insulated wire. Now, the insulation just refers to the plastic type of material over the copper, not shielding. So the wires themselves are twisted together, and that in and of itself does provide a little bit of shielding, but not very much. And then they are simply encased in the sheath made of plastic. But again, no shielding for the twisted pairs, hence the term UTP, unshielded twisted pair. So its counterpart is shielded twisted pair, or STP. So we see the same basic structure, but each pair is insulated by a metallic shielding such as foil. And again, the foil helps to reduce electromagnetic interference. So that's a plus, of course, but the downside, it was more expensive. Now, when it came to the twisted pair cables, they were divided up into several categories based on their specifications, and we'll take a more detailed look at all of these later on. So for the time being, at a basic level, Category 1 was voice only, essentially phone cable, a maximum data rate of 1 megabit per second. Category 2, a 4 megabit per second token ring implementation. Category 3 is where we start to see the beginnings of what we might call standard Ethernet. 10 base T was another name for the cable, and that actually stands for 10 being 10 megabits per second, base being baseband transmission, as opposed to broadband. Broadband is a variation of frequencies. Baseband is effectively 1 and 0. And T for twisted pair. So a very common name for Category 3 or Cat 3 cable, as you might refer to. Now, it did actually have a maximum data rate of 16 megabits per second, but that typically was only over very short distances under perfect conditions. So overall, you could expect 10. So again, the name, 10 base T. Category 4, 16 megabit per second token ring. Again, a maximum of 20 over short distances, perfect conditions, things like that. But in general, you could expect 16. And Category 5, or Cat 5, you may have heard the term. This is where we start to see what you might think of as modern Ethernet. It had a maximum data rate of 100 megabits per second over 2 pair of wires, but a gigabit over 4. And that's actually something that should be mentioned. In the previous graphic, we saw that there were 4 pair of wires, but in fact, only 2 of them were used up until this point. And that was, in essence, in anticipation of future refinements and enhancements to the cable type. So finally, the 4 pair came into play, and we start to see gigabit transfer rates. 5E is still gigabit Ethernet, again with a maximum data rate of a gigabit per second, but over 2 pair instead of 4. Category 6, also gigabit Ethernet, and also a gigabit per second over only 2 pair. So that does not seem to be any different than 5E, but it generally came down to the distance over which you could still achieve those speeds. So Category 6 was a little more efficient at consistently carrying gigabit Ethernet over larger distances. And then we see 6A and 7, capable of handling 10 gigabits per second. Now, it says experimental. That's not so much that it's not available. It's just that some of the specifications aren't entirely complete, and you may not exactly get that kind of transmission rate all the time. You're going to see variations, depending on a number of factors. But it does have that capability, if you will. So as things refine and improve, you will start to see that become a little more reliable in terms of its overall speed. Now, again, we'll talk about the categories in greater detail later on, but those are some of the basic categories available today. Fiber is, of course, transmitting the information using pulses of light as opposed to electric signals over a copper medium. The fibers are surrounded by glass or plastic, often referred to as cladding, and the benefits include very high throughput, very high security because it's almost impervious to tapping. Once you break into the wire, you effectively lose the signal, and very high resistance to interference. It's just light, so it is far less susceptible to any kind of interference. Now, there's a few different implementations. Single mode fiber, or SMF, has a very narrow core, 8 to 10 microns in diameter, and can accommodate high bandwidths and long distances, so many miles. So you would see this, for example, in modern day fiber optic implementations to people's homes, where you have to travel a very large distance to get there. Now, its counterpart is multi-mode fiber, or MMF, which has a larger core than single-mode fiber, 50 or 62.5 microns, and pulses are generated by laser or LED, and they travel over the core at various different angles. So, in other words, there's a lot of reflecting going on. But with this, it means that it's not suited for lengthy installations, such as getting to a person's home. But that's fine, because it's less expensive to install. It's often used to connect network appliances, such as connecting a router to a switch on the backbone of a network. So we are much more into the LAN environment here. So the amount of reflection that happens can reduce the overall bandwidth, but it's fine for shorter distances. And finally, converters are used when you have a mix of environments. You can have a bidirectional converter, which is required to connect networks using both multi-mode and single mode. So if you are using the single mode over the larger distances, then the multi-mode over the smaller, you need some point where it converts. These are also used when you are trying to connect a portion of the network using copper to a portion using fiber. So it is quite simply an adapter, but accommodates those different modes and or different physical media types. In this presentation, we'll take a look at what's known as plenum cable, which is a characteristic that has nothing to do with its data transfer rate or its distance, but rather where it is physically installed. It is actually run through what's known as the plenum spaces of a building. And this is the space used for air conditioning and HVAC systems and for effectively running all of the cabling in something like an office building. It is actually the space between the structural ceiling and the suspended ceiling. Almost every office building has a hanging tile ceiling, so it is quite literally the space between those two, or possibly below a raised floor. Same idea, but why is this a concern? Well, quite simply because it's a fire hazard. The plenum typically is wide open. Within any given floor of an office building, you have several offices. There are walls, things that could, at least for a while, contain smoke and flames, but the plenum is usually wide open for most of the entire floor. So it allows fire and smoke to spread very easily. So the cabling is much more exposed to catching fire. So the plenum cable is quite simply coated with a fire retardant substance such as Teflon, and even if it does catch fire, then it's designed to burn at a much higher temperature, and that actually helps to reduce the amount of toxic gases and smoke as it burns. The hotter the temperature, the faster it combusts, so it actually produces fewer gases. So quite simply, when you are installing cable in the plenum, it needs to be plenum rated cable. Now, the standard type of cable in almost all types of cabling is what's known as PVC cable, and this is used for both the insulation and the sheathing of most cables, and consists of a chemical compound called polyvinyl chloride, hence PVC. And PVC in and of itself is not plenum rated. If it were to catch fire, it does actually give off very toxic fumes. So you need to ensure that if you are running cable through a plenum, that it would not be traditional PVC cable. It's suitable where cables are exposed to high or low temperatures, or to provide protection against UV light to avoid degradation. And it does have the benefits of being stable, robust, and durable, but standard PVC cable is not plenum rated. Now, you can get plenum rated PVC. This has the additive so that it does resist fire in the first place or burn hotter if it does catch fire. So you need to be aware of whether or not the cable is plenum rated. And of course, plenum rated cable is going to cost more. So it's fine to use the standard PVC cabling outside of the plenum, but by just about every building code, it would have to be plenum rated when it is running through those plenum spaces. In this presentation, we'll take a look at some of the standard connector types used for copper cabling, beginning with the RJ11. Now, the RJ stands for registered jack, but the 11 doesn't really indicate much about the cable or even the connector itself. It's more of just a series number. But this is what we tend to think of when we say a standard telephone jack. Now, it was used for dial-up connections and or connecting a phone line to your modem, but for the most part, it's a phone jack. The cable and the connector itself contains 4 wires, so it was slightly smaller than an RJ45, which we'll see in a moment. But with respect to the phone connector, if you are using a fairly new phone system in an office type of environment, there is a good chance that it would actually be using an RJ45 because it is an IP-based phone. But traditional landlines used and still use the RJ11 connector. So here we have the RJ45, which for all intents and purposes is what we tend to think of when we say a standard network cable. This is by far the most common connector for LAN environments and often referred to as an Ethernet jack because that is the type of cabling used in Ethernet implementations. The cable and the connector has 8 wires in this case, so it's slightly larger than an RJ11, but they do look similar. But again, this is for all intents and purposes a standard network cable. Now, the BNC connector stands for Bayonet Neil Consulman, but you might also find British Naval connector used in some circumstances, but this was a male type connector used with 10-base-2 or even 10-base-5 Ethernet systems. Now, that goes all the way back to the coaxial cable that was also known as thin net or thick net. It was officially known as RG58AU cabling, but it was the solid copper core coaxial cable. The connector itself was a good connector. It slid on and then twisted, and that lock went over the pin to lock it in place. So it was used in the early LAN implementations, but I can't imagine you would find it anymore in a LAN environment. That said, there may be some specialized equipment still out there that do use BNC connectors. The DB9 connector, in this case, is a 9-pin connector. You can count the actual pins there, and there are 9 of them. And the D actually tends to refer to the fact that if you were to turn this connector on its side so that it was vertical, the blue portion there would actually look a little bit like the letter D. But this was designed to work with simple serial interfaces, often known as COM ports as well. They were once common with serial peripherals such as keyboards, mice, and joysticks, but you'd have to go back quite a ways to find that connector used anymore. It was superseded entirely by USB. Even some of the early personal digital assistants used this type of connector, but of course that was superseded with USB and or wireless and Bluetooth. So I don't imagine you would find too many DB9 connectors anymore, but some of those earlier serial devices commonly used the DB9. And then there was a DB25, which of course referred again to the number of pins, and the D sub connector family, again because it did still look like the letter D. But this was mainly used in parallel connections, which generally meant that there was 8 bits per cycle as opposed to 1, which is serial, and used for the asynchronous transmission of data, meaning that bits did not always arrive at the exact same time. But this was originally used to connect printers and some of the earlier scanners. So again, superseded entirely by USB, so I don't imagine you would see very many of these connectors in use anymore. And finally, the F-type of connector. This is a threaded connector, so you screwed it on, and this was also used with coaxial cable, but this was commonly used for cable TV and or cable modems. So if you did have a cable TV connection, then this very likely was the type of connection you used, and it looked a little bit like the BNC, but instead of just a twist lock, it actually screwed on, so it certainly made a very stable connection. So again, those are just some of the common connector types that you might encounter when dealing with copper cabling.
Now in this presentation, we'll take a look at some of the standard connectors used in fiber optic cabling, beginning with the ST. ST stands for straight tip. Classic single and multi-mode fiber connector that uses bayonet locking features where there's a stick and twist method of connecting to an interface. The next type of connector is the LC. Now, there's no official designation that states that LC stands for anything in particular, although it was developed by the Lucent Corporation. So some may actually refer to it as a Lucent connector, hence LC. This is a push-pull connector, meaning there's no twist, no threading or anything like that. You just press down on the plastic tabs and insert it. And it was popular with datacoms and other high-density patch applications, quite simply because it was smaller than its counterpart, the SC, and the SC generally just stands for standard connector. So this one was smaller, meaning that you could fit more of them in a more tightly packed space. So if you got that better density and a little more cost effectiveness by using an LC connector. Now, the UPC connector stands for Ultra Physical Contact, and it has another counterpart, which we'll see in a moment, called the Angled Physical Contact, or APC. But the idea behind these is that when you make a connection between the cable and anything else, you ultimately no longer have the perfect conditions that exist inside the cable itself. There typically tends to be a little bit of air gap between the two. We're talking about microscopic distances here, but when it comes down to transmissions of light, they could actually be slightly affected. So the ultraphysical contact was to try to get the contact between the two as close as possible to the perfect conditions that exist within the cable itself. So the end was actually shaped into this dome type of configuration to optimize the connection between the two jacketed fibers. And that ultimately did help to reduce any kind of reflection that might occur because of imperfections. But any reflection that did happen reflected right back toward the source. And this is referred to as return loss. So a physical contact aspect did reduce the overall return loss, but any light that did get reflected went straight back to the source. And that actually tended to cause a little bit of interference as well. So that led to the APC. The angled physical contact, which further reduced the reflection because of the 8-degree angle. There was better contact just inherently, but again, this was still a little bit. But because of the angle, any light that did get reflected, it bounced off this 8-degree angle and into the cladding. So it did not find its way all the way back to the source. So there was also less interference. So less reflection, less interference. You might think, well, why would we not always go with APC? Well, like most things that have a few more refinements in them, it tended to cost a little bit more. Now we're talking about fairly small values here in the big picture, so it tended to depend on the application, what it was that you were needing to accomplish. For example, if you had very sensitive equipment, you might well go with APC. But if you had an application that wasn't quite as demanding in terms of the loss, then UPC was probably fine, and you could save a little bit of money, of course. And finally, the MT-RJ stands for Mechanical Transfer Register Jack. And this popular little guy is for small form factor devices due to its small size. It was commonly used in networking applications, and you might also actually see this on your home internet if you have fiber as your service. But this was also commonly implemented if you were running fiber all the way to your desktops in a LAN type of configuration. So again, it depends on the application. But there's quite a variance in terms of the total number of connectors available for fiber optics because they do have a number of different types of applications. So a little extra research tends to be useful with regard to how you are implementing your fiber optic solution.
In this presentation, we'll take a look at various types of transceivers, which are essentially adapters, allowing you to interconnect different types of networking devices that are using different physical media or transmission methods. So one of the common examples would be if you had a switch that was based on copper wiring, then you could use one of these transceivers to allow it to connect with a switch that is using fiber. So the first one is what's known as the SFP, or Small Form Factor Pluggable. And this plugs directly into an SFP port of a network switch and gives you this modular interface to enable these different networking standards. So again, the copper to the fiber. This allowed you to actually adapt. Now, there is also an SFP Plus, which is just an enhanced version of the SFP, but it could handle higher data rates. This one up to 10 gigabits per second, whereas the original SFP was only 1. But it did require some additional circuitry, so you mostly found these in plug-in cards for servers. If you had a particularly busy server, for example, and you wanted it to have that better capability using fiber at a faster rate, then you might adapt using the SFP Plus. And of course, you might find them in the switch as well. Now, both of the SFP transceivers were typically implemented to supersede the GBIC, or Gigabit Interface Converter. This one did the same job, essentially converting the electric current to optical signals and vice versa. But its maximum data transfer rate was only 1 gigabit per second, and they were typically larger than the SFP. So they, in essence, superseded the GBIC, but you might still find these in certain implementations. Now, the QSFP is the Quad Small Form Factor Pluggable, so very much like the original SFP. It was hot pluggable and used for data communication applications where you needed to handle those conversions. But the quad meant that it could handle 4 different channel configurations. Now, not 4 simultaneous connections, but rather the ability to operate on 4 different channels. Now, the bidirectional transceiver, or what is often prefixed as BIDI in the name, is used for only fiber optic transmissions, and it implements wavelength division multiplexing, or WDM, the variance of the frequency of the transmission, or essentially the color of the light, to achieve simultaneous transmission on a single fiber in both directions. Standard fiber, for lack of a better word, has two internal cables, one to transmit, one to receive, and they run in opposite directions. So by implementing the variance of the frequency, you can achieve the same goal. So what you have to do with these is to set them up in mated pairs. So on one end, you are transmitting at frequency X. The mated pair on the other side is configured to receive on that same frequency. Then it transmits back on frequency Y, and the originating end receives on frequency Y. So they have to be mated, if you will, in order for this to work correctly. Now, there were two types for the bidirectional transceivers, the original SFP and then the SFP Plus, which again just handled different rates of transmission. But in terms of advantages, you could reduce your infrastructure costs because it required less cable, less tray space, and fewer patch panel ports. And finally, the duplex transceiver would allow you to interconnect devices that were using different duplex configurations. Recall that a duplex cable, as I just mentioned, had two fibers. They were joined together by a thin connection, but one to send in one direction, one to receive in the opposite direction. But with respect to duplex, there were two types, half duplex or full duplex. And half was sending and or receiving in both directions, but only one at a time. So you had to take turns, if you will. Full duplex is sending and receiving both at the same time. So the duplex transceiver allowed for these different types of devices that were using different duplex communications to still communicate with each other. So it was able to adapt half duplex to full when necessary, or full to half when necessary. So ultimately, all of these transceivers were really just adapters to allow you to integrate these various components and hopefully save a little bit of money by not having to upgrade all of your equipment to these newer standards. In this presentation, we'll take a look at what's known as the termination point for network cabling. Now, the idea behind this is that, of course, if you look at any office environment, you will likely see a data port on the wall or a phone port, depending on how new your environment is. There could just be a data port that's used for both phone and data, but the point is that throughout any given office, those jacks are on the wall in just about every office or every cubicle, everywhere that somebody works. So they're scattered all over the place. The other end of that cable needs to terminate, hence the term, at the same place for easy, convenient access to all of the connections. So it's just a way to centralize the other end of the cable. So if you can imagine yourself being able to walk through that cable, if you walked in the port on the wall, you would come out at the termination point on the other end, and so would every other port. They would all terminate at this same point. So this first one is what's known as a 66 block, and often you'll hear the term punch down block used as well, because the wires were quite literally punched into place, and we'll actually see the tool used for that in a moment. But these ones were commonly used for telephone cross-connect devices, and the term 66 is actually just a series model number. It does refer to the type of insulating wire around where the connection itself was made, but it doesn't have anything to do with the number of wires that were used to connect, because you see it supports 50 pairs of wires. So they were connected to the terminals using the punch down tool. In fact, this is the tool here. They were quite literally punched into place. So again, it was wired to the wall jack on one end, and then it was just left hanging temporarily until all wires were run. And then they were just basically stripped a little bit at the end to expose the actual core wires, which were then punched into place so that insulation was pierced and the connection to the block was established. Then there were separate jumpers to connect each block together. So effectively, what you ended up with was the ability for all of the phones, let's say in any given environment, to be able to communicate with each other. So particularly internal phone systems had the ability to call anyone else just by dialing an extension. And this more or less facilitated that capability. Now, you would typically see the ends at that point connected together with something like a PBX, or what's known as a private branch exchange, which of course also allowed you to make calls to the outside. So there usually was something else in addition to the punch down block, but that did at least facilitate the ability for internal communications. And you can kind of really think of it as a switch for phone systems, so that you could dial the number of any given system and they were all cross-connected at the termination point so they could communicate. Now, from that point, the 110 block was released, and this quite simply facilitated larger environments. So it's still a punch-down media type, but this one also could support data networks. So again, this is where things got a little newer. Most modern phone systems in most office environments are actually using something like Category 5 Ethernet cable. So this was able to support that type of cable and more pairs of wires. You can see from 25 up to 500. And it still used small metal jumpers to bridge any connections between any two devices. But both the 66 block and the 110 block were effectively superseded, if you will, by the patch panel. Now, really what this is it's still kind of a punch down block on the back side of it. So we are looking at the front side in the graphic, but now we see a plain Ethernet connector used. So again, you'd have bare wires that were punched down into the connections on the back, but this allowed us to just put a switch into the same rack where we mount all of these and just run a plain old Ethernet cable from the patch panel to the switch. So if we just look at the first 8, for example, let's just go with small numbers. If you had 8 data ports on the wall, they would all terminate at this point, 1, 2, 3, 4, 5, 6, 7, 8. Then you mount your switch and you simply run Ethernet cables from 1, 2, 3, 4, 5, 6, 7, 8 to the first 8 ports on the switch. That now provides the switching capability so everybody can communicate with everybody. But this was much cleaner, much neater. You didn't see the exposed wires. They were all in the back. So again, it was just a matter of plugging in the cable to allow everybody to see everybody. So this way, it was easy to reconfigure. You simply move a patch cable to reassign a network line to a new switch port. And aesthetically, it was much neater, much cleaner looking. You could tie wrap all of the cables together running down the sides and then just move them into the appropriate port. And if it had to be moved, you could do that quite easily. Just, move any Ethernet connection from the patch panel to a different switch, for example, and you could connect to a different LAN or a different VLAN or something along those lines. And you could also do the same with fiber. There was a patch panel which is simply used to terminate fiber optic cables, pretty much the exact same thing, just for fiber. But it could also be used as a distribution panel, a multi-fiber cable split into individual cables. Now, the multi-fiber cable really is just one large cable with many smaller cables inside of it. So it was just a way to make a lot of cables fit into a nice, easy to run, easy to implement configuration. So again, from the perspective of seeing it running along the walls and up through the ceiling and things like that, it was just a single cable. But when you connected it to this device, it split them off into multiple cables. So again, just a little bit easier to run when you had several systems that were more or less physically close together. But ultimately, the termination points are really just to centralize everything. You've got those wall jacks and those data ports spread all over the place. I want to be able to deal with the central connectivity of all of those devices in one place. So they all terminate in the wiring room or the telecommunications room. And again, then we can use the appropriate device, a PBX or a switch or whatever it is, to cross-connect every device. Now, in this presentation, we'll take a closer look at some of the copper cable standards for twisted pair cabling. And we'll start with Category 3, because the original Cat 1 was purely for just phones. It really was not used in networking. And Category 2 was the original token ring, which is virtually extinct. So Category 3 is the unshielded twisted pair, or UTP, and it is actually commonly used in telephone wiring these days. In other words, as I just mentioned, Category 1 was for just phones. But a lot of modern phone systems in most offices these days actually use the IP network. So they are voice over IP systems, and as such, they use the actual Ethernet network. So Cat 3 was designed to carry data up to 10 megabits per second, which is not very fast by today's standards, but it is more than adequate to handle voice data. So the other reason it's commonly used in phone systems is because, again, by today's standards, since Cat 3 is rather old, it's very inexpensive, comparatively speaking. So you don't really see Cat 1 even really used for phone systems anymore. We see Cat 3. So it's a modern implementation of a phone system using this newer cable specification. Now, Category 5 is a high-performance multi-pair cable, still using twisted pair conductors, that is used primarily for data transmission and originally offered speeds in Ethernet of up to 10 megabits per second and then ultimately got to 100. So this is where we started to see what we used to refer to as fast Ethernet, really separating itself from the original Ethernet and also from token ring, which never got faster than 16 megabits per second. So certainly the higher data rates that we expected to see in more modern networks. Then we saw Cat 5e, which is enhanced Category 5, and this was designed to support full duplex fast Ethernet and even gigabit Ethernet, typically used in networks that could carry both 100 megabits per second or a gigabit per second. So again, now we are really seeing the performance improvements of Ethernet. And then Category 6 is even higher performance than Cat 5. It has reduced crosstalk and system noise. Now the speeds were comparable, but typically Cat 6 could carry that speed over longer distances. So it was a little more reliable in maintaining the speed. And the components were backward compatible with 5e, 5, and 3. So if there were some older components, then that was usually fine. Then we see 6A, which is a 10 gigabit Ethernet, still using twisted pair cable, but it extended the usable bandwidth to 500 megahertz, which was double some of the previous implementations. But as such, it requires closely matched components. The patch cords, the connectors, all need to be 6A, so you lose some of that compatibility. Now, typically, one of the main differences between 6 and 6A was the shielding, as you see in the graphic. It was possible to get unshielded 6A, but almost all implementations of 6A came by default with that shielding. So again, it reduced the interference and the crosstalk and was just better capable of supporting the higher speeds over greater distances. Then we see Cat 7, now a recognized cable type in ISO 11801. That's the International Standards Organization. It again increases the frequency range of 1 to 600 megahertz and can carry reliably 10 gigabit speeds over 100 meters. And it is only available in shielded twisted pair cable form. Typically, you'll find this implemented as a standard in Europe, but certainly is becoming more common. But of course, as one of the newest specifications, it is more expensive. And finally, some of the solid copper core implementations include RG6. This is that larger conductor that we used to see in coaxial cable, and for all intents and purposes, this is still coaxial cable. This provides better signal quality than does the twisted pair, but it's a little more rigid and a little more difficult to work with. But it's still commonly used in CATV, which is officially Community Access or Community Antenna TV, for all intents and purposes, cable TV. Satellite dish connections, TV antenna, and even broadband internet might still use this cable type, although that is becoming less common. And then RG59, still commonly used for cable TV connections, but it had a lighter gauge, and it was a little more flexible, a little easier to work with. The thinner insulation and the lesser shielding made it simpler to work with and install, but it did have that smaller conductor, so it did affect the signal quality, but it really came down to the application. It was more than adequate for some of the lower frequency signals, so if it was under 50 megahertz, then it was usually fine. But if you had the higher frequency signals above 50 megahertz, then you typically might want the RG6. Ultimately, it comes down to the application. In terms of Ethernet LAN networks, we typically do not see the solid copper cabling anymore. But if the application calls for it, it is still certainly applicable and may still be used for certain types of implementations and certain types of equipment. In this presentation, we'll take a look at several different types of clouds, known as a private cloud, a public cloud, a hybrid cloud, and a community cloud. Now, beginning with the private, this uses a proprietary architecture that is dedicated to a single organization, hence the term private. It can be ideal for businesses with dynamic or unpredictable computing needs, or just businesses that require more direct control over the configuration. The idea typically is that you would have a fairly large organization that already has, let's say, a corporate headquarters or a fairly robust data center in place, and then multiple smaller branch offices. So rather than investing in separate and independent infrastructure configurations for each of those branch offices, they will simply subscribe to the infrastructure available in the corporate headquarters. So it looks just like a cloud configuration from any given user's perspective, in that there really is no infrastructure in the branch office, but it's all under your control. So as a single organization, you manage and maintain and implement everything. Hence the term, again, private cloud. So the advantages here, certainly security. Everything remains under your control. So that has traditionally been a bit of a hurdle with respect to public cloud services, because there is an awful lot that is not under your control. Performance, you can have improved transfer rates because you can use dedicated lines and connections. And of course, management. Things such as customized hardware can be implemented where that might not be an option in a public cloud configuration. Now, the disadvantages, certainly higher costs. You do have to make that investment in the hardware and the personnel, at least at the corporate headquarters. But a lot of organizations already have that in place. But there is still the ongoing maintenance. At the data center, there can be very high demands with respect to power, cooling, and damage, of course, to power surges or any kind of weather damage or any sort of natural disaster. So then the public cloud is a platform in which service providers are used to offer their infrastructure, their resources, their applications, their storage, and a tremendous number of other services. But these are made publicly available to anyone. So we have any number of customers subscribing to those services. Advantages here, certainly cost savings. The organizations are not required to purchase, install, or maintain servers or any other equipment. And it's also what's known as a multi-tenant environment, meaning there are multiple customers that are all sharing the computing resources. Now, you might think, well, that's a bit of a disadvantage, but most of the large-scale providers have tremendous amounts of physical resources available. So with respect to what you need, in most implementations, it really can be considered to be almost unlimited. So really, that's not so much of a concern. In terms of disadvantages, however, there is limited control over privacy and security. And again, that remains a stumbling block for a lot of organizations. It's just not recommended for sensitive applications or information. The data does not reside under your physical control. There can also be limited flexibility. The platform depends on the platform provider. Now, that said, these days, most of the large-scale providers do offer an awful lot of flexibility, but there can still be some limitations whereby provider X simply does not offer the service you need. Then there is the hybrid cloud, which is a combination of both public and private clouds. This helps to maximize the efficiency and the performance, and is certainly gaining in popularity as it offers the benefits of both the public and the private models. So if you already have a private cloud and you are perhaps looking to extend, well, you can consider the public cloud as the extension, if you will. You can see that you can bridge the two and implement workloads that quite literally span both, so that if you need to offer very private services within your own organization, that can be done in the private portion. But if you need to make various workloads and services available to the public internet, that can be done in the public portion. So it does have similar advantages to just a public cloud. It is very scalable. Again, the providers have effectively unlimited resources. So when you do decide to extend, those resources are there. It can be more cost efficient because, again, you aren't expanding your own environment, so you don't have to invest in that additional hardware. Better overall security and greater flexibility. Basically, the fact that you can keep whatever it is that you need to keep private on the private side. Then anything that needs to be made publicly available can be offered in the public side. So you have that flexibility and enhanced security because you have better control over which data resides where. But again, there are always disadvantages. There can be an infrastructure dependency. There might be some compatibility issues with what you have internally versus what you need externally. And again, there can always be some security concerns, possible security breaches when utilizing the public cloud side, for example. There might be some kind of a avenue into the private from the public using the connection you have established. And finally, the community cloud is more of a collaborative effort wherein infrastructure is shared between several organizations. So what you see is perhaps a partnership of various internal private organizations, just all getting together, if you will, to share these services. So there are still concerns. There can, still be security issues, compliance issues, and jurisdiction issues. In other words, who looks after this aspect of that service? So these aren't nearly as common, but you can still see these types of implementations, and they can be a combination of private and public as well. So you may see some hybrid configuration within the community. So there can be a fair amount of overlap, but in essence, this is typically some kind of cloud configuration between a collection of organizations. But again, they certainly aren't as common as the private or the public or even the hybrid. In this presentation, we'll take a look at a characteristic of twisted pair cabling that has been defined by the TIA/EIA 568A and B designations. Now, that stands for the Telecommunications Industry Association / Electronics Industry Association, although you may see the word alliance sometimes when you see EIA. But they designated these as 568A and B. We'll see B in a moment. But it comes down to the physical arrangement of the wires themselves within the cable. Again, there are 8 individual wires twisted around in 4 pairs, but the placement of those wires is actually important when it comes to what you are connecting on either end of the wire. We'll come to that in a moment, but for 568A, you can see the pin number or the wire number, and then the associated color. So there are always the 4 solid colors of green, blue, orange, and brown, and then there are associated white wires with the same colors striped around them. So this is simply to keep track of which wire is which from one end to the other. Now, 568B only changes the green for the orange. That's it in terms of physical differences, but I do believe in terms of application, there are some backward compatibility issues with some older technologies, but in modern day LAN environments, I don't think that would be an issue. I would think the only thing to be mindful of is that if you had a box full of 568A and a box full of 568B cables, you should probably try to remain consistent. In other words, use only the A or only the B. I do believe B is the more common these days. But why is this arrangement important? Well, because 4 of the 8 wires transmit and the other 4 receive. So when you are connecting 2 devices on either end, you have to ensure that you are transmitting to the receivers and receiving from the transmitters on the other side. In other words, you can't transmit to transmitters and you can't receive from receivers. So the physical arrangement of the wires is important. Now, the first example of which 2 devices are sitting on either end is the straight-through cable. So this is 568B, and a straight-through, for all intents and purposes, can be thought of as a standard cable, a normal, regular Ethernet cable, if you will, and it's used to connect a computer on one side to a central connection device, such as a switch or a hub. So with the hub being on the central side, if you will, its wiring configuration is set so that it knows to receive from transmitting wires, and it knows to transmit to receiving wires on the other end. So this is by far the most common. You have to ensure that all of your computers connect to all of your switches with straight-through cables. But in some cases, you actually might want to connect 2 of the same type of device together, including computer to computer, or perhaps more commonly, switch to switch. Things along those lines. So if it's the same device, then the wiring is the same on both sides. So your computer and its network adapter is no different than my computer and my network adapter. So the same 4 channels are transmitting as are receiving. So if I tried to use a straight-through cable to connect your computer directly to mine, it would not work. Now, that said, hold that thought for a moment. The crossover cable handles the crossing of the wires, and it does it on a pair-by-pair basis so that you are transmitting to receivers and receiving from transmitters. Back to the hold that thought statement. A lot of modern interfaces, newer devices, can actually sense the fact that there is a direct connection using a straight-through cable, and it can digitally handle the conversion. So you might not encounter that issue with newer equipment, but in the older days, it just wasn't an option. So the crossover was straight device to device, computer to computer, switch to switch, things along those lines. And finally, the rollover was a complete flip from one side to the other. So it is entirely the opposite on one end as it is on the other. And this cable was typically not used to carry data, but rather to simply establish an interface. For example, if you need to configure or program your router, this is the cable you would use. You would simply connect your computer directly to the router, and that would give you an interface. It was often referred to back in the older days as a null connection, or a null modem cable was used, and it just turns your computer into a dumb terminal, basically, just something you can use to see the interface and type in commands, but all the processing was happening within the router. So again, it's just an interface cable, not meant to carry data in a true networking fashion, if you will. So again, the placement of those wires is important, and you can tell the difference between them by simply taking the two ends of the cable and holding them right next to each other, so that you can see the arrangement of the colors. And if they are consistent on both sides, then that is the straight through. And then if you see that complete difference from one side to the other, completely opposite, that's the rollover. And if it's different on a pair per pair basis, then that is the crossover cable. And each one has its specific implementation. In this presentation, we'll take a closer look at the characteristics of twisted pair cabling as indicated by the components of its name. So beginning with 100 base T. For starters, this was defined by the IEEE 802.3U and was nicknamed Fast Ethernet. So again, we see Project 802, and the 3 defined all of Ethernet. But of course, that was a very long time ago, and everything has been improving ever since. So the U represents one of the refinements, this one being Fast Ethernet, and it was dubbed as such because it supported a data transfer rate of up to 100 megabits per second, which was 10 times faster than the previous implementation, which of course was at 10 megabits per second. So there we see the first component. The 100 of 100 base T refers to its speed. But then we have the baseband transmission versus broadband. And we touched on this earlier, but effectively, baseband means that you can use 100% of the available bandwidth for your communications because you are not competing or sharing that medium with anyone or anything else. There's your computer on one end, there's the switch on the other end. That's it. So you can use 100% of the available frequency range of that cable for your transmissions. So basically, the 0 value would be at the lower limit, the 1 value would be at the higher, because that's all you're doing. You're sending zeros and ones. With broadband transmissions, you are typically sharing the media with other systems, other applications, other services. So what you have to do is tune in to a specific frequency. So broadband has a variation of frequencies. You have to tune in to the right channel, if you will. So again, baseband uses every bit of it as opposed to just some of it. And because you are not sharing it with anyone else, you can use 100% of the available bandwidth. So then the T referred to the cabling scheme and originally simply meant that you were using twisted pair. But 100 base TX meant that you were only using 2 of the pairs. Recall that in fact there are 8 wires in total, but only 2 were used originally. So then 100 base T4 means that 4 pairs are being used. You're now using all 8 wires. And then 100 base FX actually used fiber. Then we saw 1000 base T, or gigabit Ethernet. Over copper wire specification, this is defined by IEEE 802.3AB. And of course, the 1000 indicates 1 gigabit per second data transfer up to 100 meters. And that's a fairly standard value still in Ethernet networking, about 100 meters before you have to repeat or boost that signal. But the benefits, it was easy to implement and it was entirely compatible with older networks, so you could still actually have both. Now, you would only get gigabit transfer rates over the sections that had equipment that supported it, but you would still get the benefit over the backbone, if you will. And if you still had slower implementations from the switch to the computer, You certainly didn't see the overall increase, but it was still better. Now, 1000 base LX is still a standard for gigabit Ethernet networks, but the L actually refers to long and indicates that this version is intended for use over long cable runs. So typically fiber optic cabling, when you maybe had to run the cable between buildings on a campus, or maybe still within a building, but a fairly large one. So, maybe crossing 50 or 60 floors of any given building, that would certainly exceed the 100-meter limitation. So conversely, there was SX, and this is still a standard for gigabit Ethernet networks, but the SX stands for short. So this is intended for use with short wavelength transmission. Now, that did translate into shorter physical distances, but it was more so the fact that it referred to the wavelength. But recall that a shorter wavelength, waves that are closer together, such as 5 gigahertz, do not travel as far as longer wavelengths, such as 2.4. So it referred to both the distance that you should cover and the wavelength. So that depended on the application, but effectively, this was for short fiber optic cabling. Still an extension of the standard Ethernet technology, again for gigabit level network speeds, just over shorter distances. And then finally, 10G base T is 10 gig. So this is still 802.3, but AN as defined in 2006. So again, the 10G refers to the speed up to 10 gigabits per second, and it supports transmission over twisted pair cabling, either shielded or unshielded, but shielded would be a little bit more resistant to interference, and still up to 100 meters for reliable rates. But ultimately, when you look at the cable and you see a number, then the word base, then the T or the F, you know what that cable is all about. The number is the speed, base is baseband transmission, and that's consistent for all of them. But then the T for twisted pair, or the T4 for 4 pairs, or the F for fiber. So in essence, they are descriptions of the characteristics of that cable type. All right, for our exercise this time, we'll ask you to describe the various media types, then to list the various connector types, then to recognize the different copper cable standards, and finally to describe the available Ethernet cable transmission standards. So as per usual, what we'd like you to do is take a few minutes, pause the recording, and jot down some responses. Then we'll come back to review, and we'll see how you made out. So we'll see you shortly. All right, so to review, we first asked to describe the various media types, and we saw coaxial, unshielded twisted pair, and shielded twisted pair in categories ranging from 1 to 7, which we'll also recap in a moment, but they were the copper types of media. Then we also saw fiber, which was available in both single and multi modes. Then we asked about the connector types, and for copper, we saw the RJ11 for phone connections, RJ45 for standard Ethernet network cables, the BNC for coaxial, then DB9 and DB25 for serial and parallel port connections, and the F-type, which was also for coaxial cable, but typically a threaded connector where a BNC was a twist lock. And the F-type coaxial was generally for cable TV or cable modems, where the BNC was for the older thick net and or thin net types. Then in fiber optic cabling, we saw the LC connector, then the UPC or ultra physical contact, and the APC or angled physical contact, and then the MTRJ, typically for small form factor devices. Then we asked to recognize the different copper cable standards, and these are the various categories we discussed, typically starting at category 3, because below that we're generally dealing with phone connections. So 3, 5, 5E, 6, 6A, and 7 were the twisted pair categories, and each one simply improved upon the speed and some of the other characteristics, but most notably the speed. And then RG6 and RG59 were the specifications for coaxial cable, but they really aren't used very much anymore. And finally, we asked to describe the available Ethernet cable transmission standards. And this is where we saw, again, the speed primarily of the cable. So 100 base T was 100 megabits per second, baseband transmission, T for twisted pair. Then 1000 base T is simply a gigabit per second. Then the LX and SX were longer versus shorter runs. And then 10G is, of course, 10 gigabits per second. So hopefully you made out all right with those review questions. And if so, we are ready to move on to our next course.